So good morning. We are going to start because we have a lot of things that we are going to cover, or Étienne is going to cover, and we also want to leave time for discussion and questions. So Étienne is an associate professor and permanent researcher at CNRS in France, and he specializes in political sociology and published 2 books. And we are really excited to have him and talk about a topic that is really very important and sort of came to the scientific focus in the last couple of years, which is the use of machine learning and in the social sciences. Étienne is going to give a presentation, and if you have any questions, please write them in the chat. And then after Étienne finished, we are going to address those questions to Étienne, and then depending on how much time we have, we might do some give and take as well, where the audience can pose questions directly. But for now, we are going to start, and Étienne, please take it away.
All right, thank you, Akush. Thanks for everybody.
All the audience should mute their
microphones, otherwise we're going to have some parasite noise, yeah, which can be welcome. Hi everyone, good day. I don't know where you are. I am in fact in Paris, and as Akush said, I'm a researcher at CNRS. So for today's session, you know, the SASE leadership asked me to talk about artificial intelligence or machine learning. I'm going to use both terms somewhat indiscriminately, although there may be some differences between the two. And what I'm going to do today in the spirit of this workshop is, yes, going to basically ask one question, and the question I'm going to try to answer or to go through with you is, should we as social scientists care about AI? There's a few remarks that I should be doing before that. The first one is that I need to say that I am a practitioner, but certainly not a specialist of machine learning. In fact, I am a political sociologist. I study social movements, political elites, state, and I do archival work, ethnography, interviews, and sometimes when I need it, I do quantitative methods, but only when I need them. So certainly not the point of view of a statistician that I'm going to give today. But recently, let's say in the last 5 to 7 years, you know, I have gotten interested and turned my attention to machine learning or AI. And I have embarked in a journey to make a few machine learning experiments and to use machine learning, you know, when I need it. So what I'm going to try to do today with you is to take you along this journey that I have traveled recently, and to sort of like give you the idea about what I take from this trip. Before I get further, there's 2 other slight disclaimers that I would like to make. The first one is that I'm going to talk about what AI can do for quantitative methods in sociology. I'm not going to talk about sociology of algorithms. I'm not going to talk about biases in algorithms. These are arguably very important topics, in fact, probably more important than what I'm going to talk about today. But this is not, you know, the purpose of today's talk. Although, of course, if you are interested in the latter topic, the sociology of algorithms, having some knowledge about the inner workings of the algorithm is something that can be useful and that I hope to provide. And also the last section of today's talk is really, you know, can be heard irrespective of your methodological inclination, whether you do qualitative or quantitative work. The last section about data production really has little to do with quantitative methods, but it's going to be a talk mostly about quantitative methods. And finally, and that may be a bit paradoxical, my talk is going to be mostly non-technical. I am going to give a sort of like broad introduction, and I would like to apologize in advance to all of you who know a lot about that and who may resent me, cutting corners, but that was probably the idea of this workshop, to introduce that with as little technique as possible. And finally, I'd like to thank my talented collaborators, Julien Bollard, Salomé Do, who have taken me along this trip and sometimes, like taught me a lot of things. All right, let's get started. So I don't know about you, but when I hear about AI these days, the impression that I have is basically the impression of a big wave that is lashing onto me. And it's true that it's been, a decade or so that AI has been virtually everywhere. Everyone starts to talk about AI. You got AI for democracy, AI for business, AI for industry, AI for growth, AI for privacy, AI for the environment, AI, you name it, AI has been basically everywhere. And just like big data, just a few years back before AI, you cannot do away, with this discourse. And as is often the case, in these circumstances where you have a sort of narrative overflow, you got some trends, that tends to stick out. And in fact, the trends that tends to stick out with AI are either the most gleeful, optimistic ones, or they're the most like dark and pessimistic ones. You have, and you hear a lot about the prophets of the good news and the prophets of doom. And in science, basically, you do hear the same positions, they're just refracted within science, but you cannot really escape such talks about how machine learning is going to change for good or bad, the way we were doing statistics. Let me give you a sense of, how that works in science. So you have one of this person whom we could arguably call, a prophet of the good news, Pedro Domingos. He's a computer scientist at Stanford, and he wrote that popular essay, the master algorithm. And when he talks about machine learning, he has, no words kind enough to describe it. Machine learning, according to him, follows the same procedure as classic statistics of generating, testing, and discarding or refining hypotheses. But while a scientist may spend her whole life doing so, machine learning can do it in a fraction of a second. But otherwise, machine learning is the scientific method on steroid. It is thus no surprise that it is revolutionizing science. Well, if you follow Domingos, the Kanagawa wave that we've seen before, the ominous wave, is nothing more than this fancy wave that we need to ride to advance, democracy, science, to go further and faster. But of course, some people beg to differ, and there's been many criticisms that have been issued towards the use of AI in science. And these criticisms are nothing new. In fact, they've been in the field, for decades. Some 20 years ago, Breiman, a computer scientist, wrote a very insightful paper called The Two Cultures in Statistical Modeling, which is highly readable and that I recommend, where he was actually making, the same remarks. So what are the criticisms that are generally made to AI? One, it is that AI functions as a black box, that AI, has a way of like dealing with data that is quite unclear. The inner workings of the algorithm are not completely understood. And this is something, this opaqueness is something that exists for people like, UI statistical profanes, but it's also something that, statisticians working in the field of AI have to deal with. It's not that we lack the statistical competencies, it's that, the reason why the algorithm works so well in details, are not fully known. And there are many experiences that have shown that to demonstrate till the end why an algorithm works so well, and not just to give a heuristics, you have to simplify it very much. So the first problem, is the problem of a black box in AI. Of course, if you have this problem of black box, and that you're a statistician, you may not like that very well. You may think that it's a bit of an issue to not understand, how the results that you get are produced. The second criticism, and that's nothing new, the second criticism is the idea of prediction, and what a good chunk of what machine learning does is that it does predict. And this is all good and well if you're a company and if you want to know why, if you want to know if someone is going to watch a movie, buy a product, sign a contract, etc. But when you're a scientist or a social scientist, you may also ask yourself, and maybe before that, of why that person is going to do that. And it is true that, at least in the first place, machine learning is not so great for doing explanation. It is better at predicting. Finally, third criticism that often comes up, is the question about the uncertain results and the lack of optimality of the results. This is something, that somewhat touches upon the first point, which is that the results are not fully demonstrated, that we may end up in situations in getting results which are unoptimal and not knowing about that. And of course, if you're a statistician, if you're a scientist, you may not like that either. So these are the main criticisms, that are faced, that AI is faced with. There's also a bunch of external criticism that people tend to make. One of them is that AI has a sort of restrictive definition of intelligence, because it tends to promote algorithms that are going at best to mimic human behavior. And so in that sense, some people consider that AI is quite limited, and they ask the question of what type of learning is machine learning. It's kind of a poor intelligence. And there are other criticisms, which focus on the fact that the algorithms that we use, they're trained. And by being trained, these algorithms, by being trained by humans, maybe just a front, a name that hide and a technique that hide the fact that, throughout the process, it is something that is deeply human and that there are humans in the machine. Antonio Casilli recently wrote about that, and showed, or at least defended the idea that what happens, in machine learning is mostly, what happens with humans, and that the machine is just, and the name of machine learning is just a way of extorting, the labor value of the workers that are operating throughout, before, during, and after the process. So in that sense, there's a lot of criticisms. And if you are on that side, the big Kanagawa wave from before looks more like, the deluge, the biblical flood pictured here by Gustave Doré. So what are we to make of that? What are we to think of that when we want to use machine learning as social scientists? What I'm going to try to do today with you is not to reconcile these two sides, not to give, one side an advantage over the other, but rather to present the relative strengths and weaknesses of both techniques, the classic statistics, the now termed classic statistics, and the new statistics, although they're sometimes not so new, in the name of machine learning. And my argument is going to be twofold. The first one is that there is, between the two approaches to data, the classic one, the new one, some sort of relative incommensurability, in the sense of Thomas Kuhn, between the methods. That is to say, they ask somewhat different questions, they produce somewhat different outputs, they function somewhat differently. And so you cannot replace one by another without losing information, without being able to answer certain types of questions. And so the fears of a great replacement, for better or for worse, that is often advanced, is something that I don't foresee for the next future. And this is something, this argument is basically an argument about pluralism, that we need to have different techniques to tackle data differently according to the situation. And it could, be seen as a very ecumenical and arguably slightly boring one. But it's true. And I think that, this is something that is very much the case. But to not leave you on this just ecumenical plea, I'd like to argue, and that's going to be the second part of the talk, that the main opportunity that machine learning offers to us is not a tool to analyze data, but in fact, it's a tool that can help us produce data. And I'll try to explain in the latter part of this talk what I mean by this somewhat heretical statement: we should use a machine to produce the data. The way I'm going to proceed is that I'm going to make a few remarks, about machine learning. Then I'll move to talking about differences in practice, and I'll show, on examples how we deal with the data and to which effect. And finally, I'll move to this question of whether we should use machine learning to analyze or to produce data. All right, let's get started. So I'm going to make a few scattered remarks, and that's nothing more than a few scattered remarks to just posit the landscape a little bit. The first question that is often asked, especially by historians, is when did that start? And historians, of course, disagree about when this did start, but they agree on the idea that it started around World War II. One of the good reasons for that is that before that there were very few computers, and so it was very hard to have machines that would replace humans for that task. What people generally agree on is that there's been a few landmark moments, and one of these moments that is often mentioned is the Dartmouth seminar gathered by John McCarthy, a computer scientist, in 1956. And in the letter he sent to the people whom he invited to participate, he expressed this idea that we should, as humans, try to make machines that solve problems that so far only humans were able to solve. And so to have machines that are going to mimic, in a way, human behavior in the way they learn and in the way they deal with some issues. From there, the history which is being written and has already been written about goes in very many different directions. It's very important to notice when we think about AI that there's been many disconnected initiatives because it, of course, got developed into computer science, in statistics, but it also got developed into industry, into the booming field then of operation research, into engineering. And so, you have all these endeavors, that run somewhat parallel during a series of years, or series of decades, in fact. This, would make it for a very interesting history to be written, but also it accounts for the fact that, you sometimes have a flurry of names that are mentioned when we talk about AI. You have, of course, artificial intelligence, but you also have machine learning, but you also have statistical learning, but you also have sometimes pattern recognition. And all these terms, which do not exactly indicate the same subsection or the same object, are sometimes used in a sort of interchangeable way or in a quasi-synonymous way. And so this also adds to the complexity of evolving in this field. Second remark that needs to be made is that the development of the field was certainly very uneven. It is often said, by the actors of the field that there's been a succession of AI summers, periods when there's a lot of interest, investment in it, and AI winter, where just a handful of researchers in an underfunded lab, keep the torch alive and continue to talk about and research about AI. So there's basically three big phases of boom. The first one from the late 50s to the late 60s, with a fascinating amount of interest, news magazines, covers, money being poured on, graduate students flocking to research in AI. And this all went bust, by the late 1960s, when the promises that were being made at the time were not, met. And after this first phase of what was later called an AI summer came an AI winter. There's been a second AI winter back in the mid-1980s till the mid-1990s, followed by a second, AI winter. And we are now arguably in the third phase of the AI summer. We are experiencing the third phase of AI. Finally, the question I should have started with at the very beginning, the question of what is machine learning? So this is also a question that is hard to answer because, of course, there's an easy definition or a series of easy definitions that you could mention. One that is pretty early, that is attributed to a pioneer in the field, Thomas, states that AI is the field of study that gives computer the ability to learn without being explicitly programmed. So there is this learnability, this like plasticity, this ability to learn something, and they should be doing that without being fully, completely programmed. And this is something that most people are going to agree on, arguably. But besides that, there are many, many like divergences and differences. So I'm just going to mention them, quite quickly here, and we can discuss them slightly later in the talk if you want. The first one, which is a big opposition, is between the connectionist AI and the symbolic AI. I can get back to that during the Q&A if you want, but this is sort of a position that has been very structuring for the field. It is also an opposition, that a lot of people like to call into question, as for all big oppositions. There's a difference between AI and machine learning. Should we use them interchangeably, as I'm doing today in a very 2020 fashion, or should we consider that they're very different? That's, a debate that some people like to have. There's also countless applications, going into very many different directions. And so it's hard, to really point out what, machine learning or AI does, because, between self-driving car, machines that translate, recommender system, expert system, etc., you got like a series of like applications that are so diverse, that it's hard to pinpoint exactly what they do in common. There's a last distinction that I'm going to spend maybe 1 minute on because it's worth paying attention to, and it's the division between supervised and unsupervised method. This is a distinction that, in fact, even if we don't know it, we are very familiar with in the social sciences or in the sciences. Supervised method, these are methods that try to connect, to link a dependent variable to a set of independent variables. They're trying to find a correlation between these two elements. And this is something, as you will have recognized, that is very close to what we do when we do parametric regression. We try to map, a set of independent variables onto a dependent variable. So supervised is very close and can be compared to parametric regression. And unsupervised, by difference, is just having a bunch of variables. You don't separate between them. And what you're trying to do, with that is that you're trying to find a pattern in the data. So you're trying to do, to find regularities, to find lines of division between them. And that's something that we also do conventionally in the social sciences when we do either clustering or dimensionality reduction, taking a large, n-dimensional cloud of points and projecting that, into a lower embedding. All right, so how does that work in practice? What I'm going to do right now is that I'm going to defend the idea that these are really two somewhat orthogonal approaches to data, and I'm going to try to show you that on the case of supervised learning. In the interest of time, I may not speak about unsupervised setting right now, but we can talk about it in the Q&A, because I would like to focus on the last part, on the part where machine learning can help us produce data. So supervised setting, remember, what we're trying to do is to capture a link between a variable, say a wage, and a series of others, say socio-demographic properties. So if you do that in a very classic setting, in the setting of parametric regression, what you're going to do is that you're going to write an equation that puts wage on one end of the equal sign, and that puts a series of variables, informations, on the right side of the equation. And based on hypotheses that you have about the word, based on knowledge that you have, you do write that equation. You do select the variables that you are going to put in the equation. You do choose all the transformations to the data that you would want to do. You do add all the interaction effects, that you think should be added in the regression. In short, the researcher specifies what we call the functional form. So the onus is on the researcher. If you do that in a machine learning setting, you start with the same data, you provide data to the algorithm, but then you let the algorithm look itself for the best fit. You let it decide, which variables to select in, which variables to select out. You let him do all the transformation that it would take. You let him add all the interaction effects that it thinks should be done. In short, the algorithm does itself the specification of the functional form, writes the equation for you. And this is, of course, quite enticing, because you can think that, well, there's here something that's going to do the work for me. So why, not use that? But it's all the more enticing when you think that behind that there is a big promise. And this promise is that of universal approximation. What is universal approximation? It's basically the idea that if there is a correlation between two or more variables in a data set, then this variation, this correlation is going under certain conditions to be detected by the algorithm and be entered into the functional form. And this, of course, is very important because it has the possibility, if it works, to nudge us out of all of our biases, either implicit biases, we did not think that this variable could work, or ideological biases, we do not want this variable to have an impact, so we take it out of it. This is bad science, by the way, but I hear some people do it. And so basically you have like a huge promise behind universal approximation. All right, so let's look at how you conduct that in practice. To do that, I went to Sweden, because Sweden, as some of you may know, is this country which is register-based. That is to say that the state collects information on all its population and then makes it available to researchers. And so you have 9 million individuals, more than 300 variables, and this is for individuals. Then you can track who's living with whom, who's living in the same block, who's a parent of whom, etc. So this, in fact, is something that is pretty enticing and interesting for researchers. And what I did in Sweden is that I took very classic, very classic question, that of the determinants of wage. And I did select a few variables that are very well known to determine wage. The reason for that is that I wanted to test new algorithms on a case about which we have like extensive knowledge. And so consequently, I could see if the algorithm was doing something weird or not. So I did basically look at that. I did select a variable, did a little bit of cleaning up, and fast forward, I run my parametric regression, I run different types of machine learning algorithms, and I get the following results. So the results is like presented in these two panels. To the left, you got the naive linear regression, which is able to predict correctly 36% of the variance of the cutoff point, which means that with 9 variables, we explain 36% of the data set, which is a decent result if you think about it. And of course, if I was to do a less naive regression like econometrician would do, I would increase somewhat on that. And I did increase, in fact, 2.4. Now, to the right, I did use a very classic, somewhat old machine learning algorithm called random forest. And using random forest and letting run, I did achieve, a prediction score or prediction, score of 0.45. So my root mean square error was really lowered significantly by using the random forest algorithm. So to summarize that, the algorithm not only did outperform the parametric model, and it did find a better functional form, but it did that in a matter of, I shouldn't say seconds. In fact, it was probably minutes or dozens of minutes, given the size of the data set. But it did that, quite fast. And it did it without any knowledge of the data set. In fact, I could have added, and I did add more than 9 variables, but I threw in variables that I knew had little correlation with the topic at hand, the determination of wage. And I got, very significantly the same results. So this, of course, is very enticing when you see that. And in fact, it's a result that is quite classic, in the field. It is the case now that on certain data set, we do have a predictive superiority of machine learning. There's a recent paper by Matt Salganik and a whole cast of people, who ran an experiment, which I strongly recommend you read. It came out in March. It's a paper that basically tells the story of an experiment that they made. So Matt Salganik and his co-authors decided to embark into, to look at a data set that had been built and seriously worked on by social scientists. It was about like poverty, inequality, and life course. And in what they called this fragile family challenge, what they did is that they gave, the data set or part of this data set, which had been worked on by sociologists of life course, sociologists of poverty, to a bunch of people whose task was to use different machine learning algorithms. And quite often, the results were at least as good. I mean, revolving around what, social scientists had reached, in decades of feeding their models and of studying the problem. And this is all the more impressive, and the models did it pretty fast. And some of the people who are doing that not only knew nothing about life course, but sometimes knew nothing about sociology. So, in that sense, that's pretty enticing. Now you could say, okay, well, that's all good and well, but there's a predictive superiority, but we don't really care about prediction in science. And although there are some arguments to be made for prediction as some measure of the ability of a model to capture the structure of a data set, I think that in fact, that's something that needs to be stated. We cannot only just look at prediction. But in fact, there are some perks attached to using machine learning. And one of the tools you can use, in fact, reveals, which variables play the biggest role. And here I did compare, the results from what the naive linear regression, would tell you, from what the random forest would tell you, and they seem to match pretty well. It's not always the case, but in this case, they seem to match pretty well, except for the variable about age, which the random forest machine learning algorithm tends to give, a more important role. There's more perks to that. You can also empirically investigate, the effects of variable. And so that's something that can be very interesting when we want to look at the correlation or the effect of one variable on another. So for instance, we know for a fact that age has a nonlinear effect on wage. We know that age is probably going to increase, wage is going to increase a lot with age, and then it's going to plateau. And all the studies actually tend to show that, studies in Sweden tend to show that. And that's in fact why, when you write a classic linear regression, you square the age term. You add, a squared age term to take into account that. But of course, using a linear regression, you cannot exactly do that because the effect is going to be monotonous across the data space. And so if you haven't thought about that, you're just going to think that age, tends to increase, wage tends to increase with age in a very linear and monotonous fashion. And this is something, that we know is not right. And we know more generally, that some of our variables do not have a monotonous, do not have a constant effect across a data space. We know that being, a woman doesn't have the same effect, in this or that industry for wage. We know that race doesn't play the same role in the lower tiers and in the upper tiers of society. And so consequently, you are in a situation where in the machine learning is able to actually give you some information that you may not have otherwise. So this look all good and well, but of course, the criticisms remains, and the criticisms, there are several of them. So one is that there is relative uncertainty about the results, you do away, with all the testing, but then you don't have, enough elements to do serious testing about your data. So of course, you can work on that, but it's not as clear and as established, as it is in the parametric setting. The demonstration of why the algorithm works is, as I said before, not completely obvious either. So that's also a problem. And, beyond that, there's a lot of questions that people are working on at the moment about, causality, inference, the interpretation of coefficients. Let's say that for now, it's not as stable as it used to be. Let me focus on two more points, which I think are quite relevant for what we say. The first one is that the machine learning algorithm, even if, we can move beyond prediction, tends to give results that are much more complex and much less interpretable. In a parametric setting, you write the equation, you run the analysis, you test, and then you can read the coefficients. There is no such thing as an interpretation of coefficients, as a reading of coefficients in a machine learning setting. You can try, as I did before, with a variable importance trick, to have the model tell you which variable it thinks is more important, but it's really nothing in comparison to what you can do with a parametric regression. So of course, that's a problem if you're still clinging to the question of explanation. What is it that plays a role in there? And another big problem, no pun intended, is the question of size. Because it is the case that these models, which tend to be quite flexible, machine learning model, they also perform well on larger data sets. And one of the reasons, I went to Sweden is not because I wanted to see their red-coated cottages by the sea. It's because they had a vast trove of data accessible to social scientists, because I had a sense that working, on data sets that are conventionally data sets used by social scientists of, a few hundreds, a few thousands, etc. Lines, I may not, in fact, have an algorithm that goes over, that does overperform a classic linear or logistic regression. So this, of course, is also a problem. Even in an era of data abundance, it is not always the case that we have data sets that are strong enough to big enough to be amenable to a use by machine learning. Or it depends which algorithm. All right, so to summarize, what I wanted to say here is that, in fact, I think that, between the classic methods and the more complex, the newer method, of machine learning, we really have two different ways of looking at data. We have a technique, where you write an equation based on hypothesis, which is very demonstrative, versus a technique that is much more, and to a certain effect, radically inductive. We have a method that is classic statistics, very parsimonious, versus a method, that is much more complex and yields interesting but less interpretable results. We have a method, classic statistics, that is demonstrated, versus a method that yields, empirically efficient results, but whose, inner workings are still quite obscure at the moment. So we really have two methods that are doing somewhat different tasks. And I could demonstrate, this trade-off between complexity and interpretability in the case of unsupervised machine learning, in the case of trying to capture patterns of data, in a set of variables. But I think I will skip that, and we can maybe come back to it if there is an interest for that later. I'll skip that because I think that what is most important is not so much to pay attention about, analyzing data with machine learning. It's of course very interesting, but it's about looking and using machine learning to produce data. And this may sound, as I said before, a little bit heretical. This may sound very strange, but in fact, what we do when we produce data is that we just use machine learning to extract information from large corpora. In other words, we leverage the predictive power of the algorithm to detect information in text, in video, in audio, in sound, etc., etc., in order to extract information. And then you can do whatever you want with that. You can read, you can do, descriptive statistics, etc. So let me illustrate that, with one example that I'm working on at the moment. With colleagues, I am actually looking at the evolutions of political journalism. And I'm doing that, with a focus on narration, with asking myself a question, how do journalists talk about politics? And of course, why is it that it has changed? So what we're doing is that we're not only looking at the journalists, the biographies, the careers, the trajectories, the salary. We're not only looking at metadata, about the circulation, about the paper, about, the shareholder structure of a journal, or about, like the number of words or, the number of times an author writes in a newspaper. We also look at the content of a newspaper in order to know how often, a certain trope, a certain way of talking about politics, emerge, and, whether it stays there or fades away. And, of course, if you want to do that over 50 years and over, 5, 10, 20 journals, you're going to be faced with thousands and thousands of articles that you'll have to comb through. So the classic solution to that, which exists in the literature, is that you're going to do some sort of more or less random sampling. You draw articles, then you read them, you do hand annotation, and then from these results, you score and you do some sort of interpolation between the years. So you take one article a year, 2 articles a year, etc., etc. So you do that, but the problem is that there may be a lot of things that happen in the space that you interpolate. Respectively, you could hire an army of research assistants, but the problem you would have at that moment is probably that you would have first to pay them, then to train them, then to make sure that they're doing their work, fourth, that you have to make sure that they agree one with another, etc., etc. So it raises a lot of other problems. The machine learning solution to that is slightly different. What you do is that you're training an algorithm so that it does the job for you. So in practice, what you're going to ask the algorithm, or what you're going to do with it, is that you're going to show it a limited number of examples to the algorithm. You're going to make sure that the algorithm has learned adequately by, predicting on a corpus that it hasn't seen, and then trying to see if you agree with it. And then once you agree, you have it predict on the whole corpus. Let me just be even more specific. What we're trying to do is to find instances in one task of, one of these trope of journalism, which is off the record. That is this process of, quoting unnamed sources to reveal the backstage aspects of politics. And the problem, you may face very quickly is that even if you have all the text, there are so many ways you can introduce off the record that you cannot list them. Of course, you got the classic as per an anonymous source, but of course you have also according to an unnamed source, an aide to the president, revealed, disclosed, said, blah, blah, blah. You can have all the expression verbs that you want, or again, person briefed on that matter, etc., etc. So the solution that you can try to, use and train is to train an algorithm. So what you're going to do is that you're going to carefully select instances of the record in a set of articles. And you are going to train the algorithm to make sure that it has learned properly by having it pass a test. And then you're going to have it, if you're happy with that, predict on the whole corpus. If you want to capture the intuition, it's nothing different than, when big companies ask you, to detect through CAPTCHA, for instance, whether this is a car, a bridge, a signpost, or a car. Basically, what they're asking you to do is to click on a bridge, a car, a cat, a road, etc., in order to train their algorithm so that later, in a different context, from a different angles, with a different light, their algorithm is able to detect a cat, an algorithm, a road, a bridge, etc. So we did that, on 2,400 instances of hand-labeled data. in one French newspaper. In practice, how does that work? Well, you have, an annotation interface in which you read the article, and every time you see an instance of the record, you highlight that. And so you got a few hours of tedious annotation. In that case, I did it, and it was around 12 hours. I'm leaving the text in French here in case there's Francophile people. But just so you know, there's 4 places where I think there is an instance of the record in this segment, which is pretty high. Then, you have, the algorithm learn, based on what you've shown to him, generalize, and then predict on a test set that it has never seen, and you look at the results. I'm not going to get into the details here, but just look at this F1 score here. It's between 0 and 1, and it means that in 79% of the cases, the algorithm has predicted properly the result that I was asking it to search for. That is to say, we agree, the algorithm and I, on 79% of the cases. And for the task that it is, it's sequence labeling, it's a pretty high score, one that is probably quite close to what humans coding, different humans coding would reach on if we were to do some sort of inter-agreement score. So it is in fact quite tedious, but it is, in the hands of an expert. It's cheaper. It's probably nicer to research assistants. And in fact, I think that in many cases, it can yield better results than you would get if you had an army of researchers. Just so that you can see, and then I'll fast forward, this is the result that you get. So you can then look at the text that is highlighted. You can score it. You can see where there are mistakes. And then you can, of course, do whatever you want. This is the last result, the plot, that you get from that, which shows that indeed in France, there's been a significant rise of prompts introducing of the record quotes in Le Monde over 50 years. More generally, you can use data. You can use machine learning to produce data to do a vast number of things that we have an interest in social sciences. You can detect the presence or the absence of women in film, people in picture, but also cars in the street, manifestants. You can look at satellite pictures, etc. And from them, collect information. But then you can either plug in a regression, use in an unsupervised setting, or just read or do descriptive statistics about. You can, transcribe writing styles. It's quite famous that the German current shrift is hard to read. Well, you can pass that through an algorithm that is able to transform that into like a modern alphabet, and that's going to probably save you a lot of time. If you're looking at videos, you can detect roles. For instance, are women, in the foreground or in the background of movies? You can detect, mood through voice inflections. You can transcribe automatically through audio, but also video. You have algorithms that now try to tell you what is the content of a video automatically, and then you could search through that. And this is the example I took earlier. You can classify according to your own classification scheme, and that is something that is very, very useful. And that becomes, all the more relevant as we have more and more data. All right, so let me conclude. I started that discussion, asking, should we care about AI? And I hope that I have at least somewhat convinced you that, yes, we should care about AI and about what is going on in this field, even if it's only as a tool and not as an object. I think we should definitely care about AI as an object, but even as a tool. And I see 3 great merits into that. The first one is to have an alternative technique, to have an alternative strong, statistical method at our disposal, probably forces us to reconsider some of our statistical routines. It is the case that when you use, the predictive power to try to, look at how people live and to look at classic results of sociology, you sometimes, have results that are surprising, that the predictive power is not that high, or that, it points to different variables than the one you were looking at. And who's right? The jury is still out about that. Same thing when you do unsupervised learning. You have very different types of results sometimes than when you use, the classic algorithms. So in a way, it forces us, to denaturalize, the tools that we had some tendency to go straight to. The second big reason I think we should care about AI is that because it's flexible, because it's more complex, it is sometimes bridging the gap between our theories and our methods. What I mean by that is that we, especially when we use parametric regressions, have methods that rely on a set of assumptions that are, very well known, but that also do not reflect exactly how we think about the social world. For instance, the monotony of the effects across the data space and its constant aspects is something that we know is constantly violated, in the social world. Meanwhile, because we have this technique that requires some linearity at some point, well, we have to use that method, which doesn't square well with the way we see the world. So using methods that are more complex, also more inductive, we can have methods that are somewhat more attuned to most of the theories that we have built about the social world. And finally, and I'm not going to spend too much time on that, you can use machine learning to extract knowledges from masses of data. And I spent the last 10 minutes speaking about that, so I won't delve into that too much. So I will stop here, and I am ready for questions, comments, discussion, and I hope it was useful for you.
Thank you very much, Étienne. This was really, really interesting and very thought-provoking. And there are some questions, and actually the question is that I too wanted to ask, but Valery Yakubovich posed, is that the Saganic piece from 2020 that you cite as evidence of the predictive superiority of ML actually reads to me, and I think to Valery, just the other way around. It actually, what it seems to suggest that there is very, very little value added by ML if you compare it to the deductive social science model.
Well, yeah, that's a great question. I mean, there's really two, ways of looking at that paper, and there's, different takes away from it. And I think, we can agree in the end. So for those who haven't read that piece, because it came out recently, it's this piece that tends to show that, that there's the big experience, the experiment that is made. They have probably 5,000, lines and a lot of variables about, who, how people were raised, and then they try to see how many people, how people ended up, faring in life. And what you're mentioning is that, in fact, one of Matt Salganik's and his colleagues' main conclusion is that the predictive power is not that high. The predictive power always, revolves around, 0.25, 0.30%. That is to say, they get it wrong 75 to 80% of the time. And that's, of course, something that needs to be said. But at the same time, they get the very same predictive power, and sometimes slightly higher than the classic, approach, deductive social sciences, as you call it. And so they're able in, a few minutes of playing with the data to do as well as experts in the field have been, feeding their model and deducing. So they don't go much beyond that, but they at least go as high. And this is something that is, I think, very important. It's all the more important than, as I said, these methods are, flexible, nonlinear methods which require a lot of data. And so when I started looking at the data, thought to myself, well, 4,500, there's almost no way, that you're going to have a much better, predictive score. Now, the question that this is asking, and that's the question that Matt Salganik and his colleague pose, and I think it's a great one, is so far, we were not predicting. So we didn't know that, our regressions were, yielding a a good prediction, an acceptable prediction for for 25 or 30% of the cases. And now that we pay attention to that, we realize that. And what does it say about what we've been doing as social scientists, in the last 5 decades, because we've been interpreting all these coefficients, which all had their stars, and they were all very significant, but they had a very little predictive power. And so the problem there is, what is the bar that we are also trying to pass? Are we trying to pass the statistical bar of p-value? Or are we trying to followed by some sort of plausibility? Or are we trying to pass the bar of predictivity? And this is a complex question, and they don't have the answer to that, nor do I. But it forces us to denaturalize, and that's why I was hinting at in the conclusion, denaturalize the way we think about that. But I do agree that the predictive power is at the same time slightly higher, and meanwhile not great.
But could I follow up on that?
Yes, please go, Valerie. Yes.
Just to clarify, because it's very important. Unlike in these predictive models, in our deductive theorizing, we claim causal effects, right? Sure. Even if we don't have prediction, we don't care. We want to identify one mechanism or one coefficient and show that it has a causal effect independently of whatever else is going on, right?
Absolutely.
So now we sacrifice that. We don't have any more confidence intervals, no causality, no nothing, and get the same prediction, right? So in that sense, there is no value added at all. Only we lose value. And so in that sense, I think it's important. Now there are interesting methods where causality is being brought back into machine learning. But again, my skepticism, and I'm really very concerned about it because I'm trying to use this method, that with social outcomes, really, I don't see how we can go with prediction, right? It's just too much going on. I did not see good results in organizational studies, which I'm more familiar with. Very hard to predict people's behavior.
Can I just add something to Valerie's point? That there is a difference between predicting out of sample outcomes in a certain data set where you randomly divide the sample into training set, and then and when you actually try to predict real outcomes that actually hasn't yet to happen, or that is truly outside your range of knowledge. And so if you look at the Saganic piece, the way that they were doing this was that they actually gave the input variables for the first panel waves, and then they did give some outcome data from the last wave. So the predictions were not really, so actually the machine actually was working with data from the future, so to speak. And I think that causality is very, very important, because one way of thinking about causality is basically a robust form of prediction, out of sample prediction. We want to have causality because we want to make predictions beyond the data that we have. And so if we give up causality, as Valerie says, we are not just sort of giving up our sort of bias towards interpretation and understanding, but we are also giving up our ability to make predictions in a real sense, really out of sample.
I mean, I fully agree with that. I mean, I'm like playing the devil's advocate here, to try to see what we can do with machine learning. But it is the case that if you have, the same quality of prediction without, having all the apparatus, that we've been slowly building, as Valerie mentioned, confidence intervals, causal inference, etc., and, interpretation of coefficients. In fact, I do agree that we're missing on something, and that was the bottom line of my talk, that we're trying to do something different, and in fact, it may be better to use the old tool than the new tool. So I will completely, concur with that. I think that what is interesting in the piece, is this idea that it sort of also asks us, you know, gets us out of our statistical dogmatic sleep to a certain extent, you know, because we were using, you know, classic regression because that was the go-to tool. And now we have another tool which tends to show us that what we are doing here doesn't predict so well and, you know, doesn't give very good results. So you can say indeed that there is, you know, like some interpretation that you can make out of that. But you know, I'm not sure that all the statistical models that we use are so good. And in fact, you know, that's just one answer, but sometimes machine learning can be useful, if I'm playing the devil's advocate too, in other circumstances. If you're working, you know, with thousands and thousands or, you know, hundreds of thousands of data, all your coefficients are going to be significant. So the problem is that then how do you select variables? Of course, you can resort to different criteria of information, but, you know, that's something that's also posing a problem. And that's because these techniques and the tests have been created in an era where we had, you know, scarcity of data. So we can, you know, deal with that. I'm not saying it's impossible. What I'm trying to show here instead, or to defend, you know, is that these are really two different ways of looking at data, and that, you know, that's quite useful, you know, once you are, you know, looking at a data set. But, you know, then you can resort to your method of choice.
So we have some other questions. One from Oliver, who says that, so one quick question concerning producing data. Mm-hmm. You showed for what we can use it, for example, counting women in movies, etc. So it's more or less just extracting data. In how far would you agree that this does not have anything to do with intelligence?
Well, I mean, that's the question I was touching upon, you know, at the very beginning. You know, it's just that, you know, this field is called artificial intelligence. But then, you know, what people put in there, you know, is not for me to decide. And in fact, you know, one of the big criticisms that is being made, as I said before, is that it's a very poor definition of intelligence. So if you want to push me this way, of course, you know, I think that I am at the same time flabbergasted by, you know, the fact that we can do that. And at the same time, you know, in agreement that it's not, you know, that spectacular. But, you know, if you move from this sort of reflection about what type of intelligence is AI to a question about, you know, what we can do with it, I would say, you know, that in fact it is full of promises, because it gives us a chance to outsource a lot of the things that we were doing before, or in fact not doing before, to a machine. And if we have ways to make sure that it works, and there are ways, you know, that we can devise, then to a certain extent, you know, that's useful. So, you know, whether you want to call that intelligence, then I don't know. And I think I would agree with you, but I think it's still a useful tool.
I would like to push a little more further Oliver's point. And this comes from this book by Richard Biernacki from 2012, Reinventing Evidence, where Biernacki argues that when you are trying to extract meaning this way from text, you are basically leaving the world of meaning. Because if something is not understandable or comprehensible for the human mind, then what you end up with is not real meaning. What you end up with is some pattern that then you have to re-infuse with meaning from somewhere else. So machines cannot read books because they don't understand what's happening. They cannot reveal hidden meanings, because meaning cannot be hidden by definition. If you cannot see the meaning as a human, then there is no meaning there. What you can find is pattern that you can make meaningful after the fact. So counting women in movies is a pattern, I mean, looks at a pattern, which then gets interpreted through some extraneous set of explanatory framework, which actually could be very different. I mean, you could explain these counts in many, many different ways. So how when we talk about meaning as opposed to intelligence, how do you see that?
Well, I mean, once again, I like, this conversation because you're playing the skeptical part and I'm playing the devil's advocate on the other hand. So it's quite interesting. I think that you're a bit harsh on the technique. I do agree that in fact, what it's trying to do is to capture patterns, and that beyond that, what you're going to make of it is really, for you to decide. And this, is, I think, the beauty of it. It's just a tool that produces information that you can use later on. So in that sense, I think that it's actually quite interesting to have, a tool that is doing that. But is it going to be something that is going to replace social scientists? I do hope not, And in fact, I think that it's quite a far cry from being there, because how do you want, in fact, to go from that to, go from patterns to infusing meanings? I mean, you of course always have to re-inject that into your own research question, research design, etc. So, I would agree with that. I think the Bernanke piece that you mentioned about text is also a bit harsh, if I may say, on what we can do with text analysis. Because, it is the case that when you look for, text, the way it's been done for a very long time is that it was looking at word after word. And in fact, this is going against all the most classic and obvious hypothesis about how language works, which is that words come in a certain order and you can't just count words, because if you do that, you destructure a language. And it doesn't really make sense to do that. You're missing out, 90% of what is going on, if not more. So that's why, I was never really fully convinced by, all the things that have been done in quantitative text analysis so far. But now, the new models, in fact, have attention mechanisms that help them pay attention to the context. So whether we're dealing with word embeddings or whether we're dealing with word embeddings put on top of other technology, they do actually pay attention to what goes on, around the text. And so there is actually more contextual interpretation, or more contextual, rather, integration that is being made. And if you look at what linguists do, linguists often said that it's quite hard to do to use machines to look at language, because machines cannot, detect irony, or they cannot detect jokes. And in fact, there's a bunch of people, actually a good, dozens of them, who are actually trying to solve these questions, and to look at ways of capturing jokes, irony, understatement, etc., etc. So to go back to square one, I do think that in fact, the question of the meaning and of the interpretation is going to remain on the interpreter and on the social scientists, no problem with that. But I think that there are more possibilities with these technologies now.
I think we have another question by Samuel, and who says that he is quite convinced by the usefulness of AI you advocate from an epistemological point of view, but he has one small question: who is going to be the most able to use AI? Corporations, states, activists, journalists, lay people, or I might add social scientists?
Yeah, I mean, that's a question, we've been battling with for a long while. It has two aspects. The first one is the question of who has the skills and the computer power and the money to do that. And it is the case at the moment, that in fact, we as social scientists are not, in a situation to do that. And it's also the case that, I've been mentioning that as if it were, like something you can do out of the box, but it takes a bit of training. I do remember 10 years ago, I was teaching courses about digital data, trying to teach students, how to collect data, how to scrape it from the web, how to extract it, how to reshape it, and how to put it in different forms. And the students, I was telling my students and my young colleagues, this is an investment that is worth doing, because in 20 hours, you know how to master these things, you know how to do that. I wouldn't say the same thing with machine learning. It takes much longer and it's much harder, which means that, we need to make collaborations. We need to interact with people whose research questions, whose agenda is very different. And so in that end, we are, deprived, I would say, a little bit, but there is worse. It's that if we think that this data, we need a lot of data to train the machine, then, the companies got the data, we don't have the data. And so long, as we do not have an access to the data of different companies, then, we are definitely losing that intellectual war, because there's no way we're going to be able to do that. That's in fact a topic that is very dear to my heart, because I advocate for a very French solution to that. I think that we should have a sort of person, the state or, authorities, agencies should have a right to collect and access the data that the companies are collecting, and they could put that in cold rooms for researchers for their own purposes too. Because if, data is the new oil, as some people like to say, then, there's no question that there's no reason why we shouldn't access that. And so I defend the idea, that we should just like we take taxes on companies, we should take a data tax, and collect this information and have access to it.
So it's really not AI that concerns you being appropriated by these companies, but data.
Oh, well, I mean, yeah, you can ask the question differently. Of course, if you're asking me what are the consequences of AI, of course, I'm very worried about that. If you ask me the question of what people are doing with AI, of course, that's what I was, hinting at the beginning of this presentation, when I was saying that we should probably, even more than what I'm talking about, spend time thinking about AI as an object, that is transforming societies, and not, looking at the tools. But it's still interesting, to look at the tools and to see what we can do, because it also gives us insight into what people are doing. So, and what tool they have at their disposal.
But here might be an interesting connection to
Sure.
yesterday's presidential address, because with big data, companies gathering that huge amount of data, making them available for research creates a huge problem of privacy. And the more data we have, the easier it is to actually find the actual person that the data refers to. Which actually also raises issues about prediction, because the more precisely we can predict, the closer we get to the living live person who sort of, or organization, or whatever our unit of analysis is, and that creates a series of questions that we did not have to face as social scientists before.
Yeah. I mean, that's absolutely true. Although that we did not have to face before, I'm not so sure for certain type of research. For instance, if you were doing research, on, it's very, trendy to do that at the moment, but 20 years ago on elites, and that you were working on fiscal return, tax returns, you knew for a fact from the address and the amount of money, you knew for a fact who was making what. It was just, a small number of people who had access to that, but in fact, they had access to it. And so there's been, dispositive devices that have been created in order to secure the privacy, and that in fact over the years have proven to work somewhat appropriately. You have, in different institutions, cold rooms, that you can go into and access the data, and it logs everything that you do. So, if you're actually, you can take the data out, and if you look at something and then leaks the information, then you're probably going to be scored. But of course, the more accessible the data, the more privacy issues that there are. And I am a fervent defender of privacy. But I do think that, we're not going to solve this problem of privacy by preventing researchers from accessing the data, because, that's only the small part of a problem. You have all these companies, which run these data lakes that have very limited concerns for privacy. And we would like forbid researchers to go into that and to see maybe what is going on in there, just because researchers would like, you know, endanger privacy. I think, you know, the trade-off would certainly not be in favor neither of research nor of like knowledge or even privacy in that sense.
Valerie asks about Macron's AI strategy, and if you can say something about that. I don't know anything about that.
Well, he actually proclaimed data sharing, right? Because the state has a lot of data. Did you have a chance to learn more about this? Is there a policy already in place to go and get some data for researchers?
So I'm not familiar with that. I know that there were, you know, like discussions about this, and I know that he had a team of people working on it and gathering, you know, scientists and computer scientists. But I really cannot speak to that with enough knowledge. I can look it up and send you an email if you contact me.
Well, I'm just curious. I'm at a SEC, not far from you. I know that there is this policy and strategy to make the data available to researchers. So France is ahead with AI. I don't know how much was put in place. So I guess I will try to figure out. Maybe.
Yeah. Okay. Well, I think not much for now.
Maybe.
But I may be wrong.
Thank you. Thank you. Mm-hmm.
So any more questions from the audience? Or anything I missed, please?
Well, if there is time, at one point I wrote, Akash, I could just maybe bring it up if, since we have a few minutes. I think in terms of meaning extraction, really there is progress and it's changing. Here I'm optimist on the other hand, because we see in translation or in chatbots, all kinds, right? There is more and more ability to build these tools that actually understand the text. Mm-hmm. So in that sense, I think there is a promise. Going back to the causality and all that stuff, in our current models, we don't predict the outcomes very well because the effects we causally try to put forward, they're small effects, right? We build a big theory around some effects. 3% increase in the outcome, it doesn't predict the outcome, right? So it's just we predict the coefficient, hopefully theoretically correctly, not p-hacking or harking, which pretty much we are doing machine learning, only don't acknowledge very often, right? That's another problem. So that's a different story, that if you do it well, if you do it causally, you estimate the coefficient well, you don't predict. But the prediction here is not the goal, right? So in that sense, the traditional approach does something different. We want to have a bit of both. And one approach I see Fanish Puranan from INSEAD promotes is inductive theorizing, when you extract correlations from these models and take the next step and actually set up a causal model and other data on which your kind of empirical insight can be tested. Right. So, and then actually derive additional implications, right? So you found one correlation, you build a theory around it, then you say, okay, if this theory is correct, then we should find other correlations, A, B, C, D. And then you pick them in that data already not based on the machine learning model. So I think that's another way in which people trying to push this kind of incorporating ML in research.
No, of course, of course. I mean, first thing, I do agree, and I think you put it better. You know that my argument was that the technologies, the two approaches are trying to do two different things, but you put it in a much better, and much more rigorous way when you said that you're trying to capture causality by measuring small effects with parametric regression. You're trying to predict, still looking at which variables may be influential, but that's not exactly the same task. And I think that's actually a very nice way of putting it. I may use that later. So thank you for that. When it comes to like the work on causal inference in machine learning, like this, as you know, like there's a whole growth industry of people working on that at the moment, trying to make machine learning explainable or and understandable. And I am like, I'm not sure that like the talk I gave today will be the same in 5 years. I think in fact it won't be, because there's so much like interest and interests monetary also put into that, with like this big DARPA grant on explanatory AI that has been given. But I think, that there are techniques that are going to be developed pretty fast, to actually mix the two problematics. And this is, what we classically called in sociology a process of refraction, or Abbott would call that fractalization, where you have the tools from, one community that are being imported but selectively into the other community. And, this may very well, lead to like assessing causality very differently, in the next 2, 4, 5 years, I'm curious.
But, if you take Judith Pearl's work, then you find there's, a more fundamental problem here, which is the nature of the math. Because what ML does is it is looking at patterns, and patterns are symmetrical, and causation is asymmetrical. And so the all these function fitting is sort of, according to Pearl, is done with the wrong assumption to extract causality. And I'm really curious, how far this research program is going to go, whether there would be sort of a replacement of some of these methods with asymmetrical function fitting.
Well, actually, there are people who integrate Pearl's approach, this causal calculus, with machine learning. There is, for example, Mark van der Laan at Berkeley, and actually his member of his team, former student, is at Paris, at the Université de Descartes, Chambard, forget his first name. So essentially, you need the model, causal model by Pearl should come from a theory. That's another reason why theory doesn't go away, at least in the near future. They talk about causal discovery, but it's a long way to go. So you bring a model into the machine learning, bring causal model into your machine learning model. But for that, you need very high accuracy prediction. This is what van der Laan argues. And since in social science, we don't have very good predictions, so it will be hard. That's how I see it at this stage.
Fair enough.
Excellent. So any more questions, or are we sort of concluding? If no, well, thank you, Étienne. This was really, really a very, very interesting and very, very thought-provoking presentation. And I'm really glad that we did this. Yeah, you have these slides. Is there any way that...
oh yeah, sorry, the slides. Let me give back that for those who came late. So you can get the slides on my website if you go to, ollion.cnrs.fr/news. I did put like the PDF version of them, so you can access them, or you can just send me an email, and I'll gladly, send anything I have to you.
Well, thank you very much, and I would like to thank also the audience, and I'll see you at other panels.